Hello everyone and welcome back. So we now have Perlin noise behind us, both 2D and 3D. And we were going to be moving into Simplex 2D noise theory in this video, but instead Lee's been doing a little bit of work off camera. We've had a bit of downtime while I was doing some other things. Lee did a little bit of exploration, and I'll let him tell you what he found and what he wants to cover in this video.
All right. What I want to show is something that came up in one of the last videos. And actually, it did show its head several videos back. That being...
Yeah, what are you talking about? I've been commenting about this for a while now.
Yeah. This artifact with lines showing up depending on where we are in the animation, where it was showing up in value noise and then it started showing up in Perlin noise. And then once we animated the Perlin noise, it became even more relevant. Well, in between our downtime, that got on my nerves and I started doing some investigation to figure out exactly what that is. So to make the problem show up a little bit more prevalently, what I'm going to do is create a couple of other variables, XO for XO, not X0, XO for X with an offset is going to equal X minus, or no, it's going to be, is it X minus? Yeah, X minus our texture size. And I can't type for the life of me right now. So texture size divided by 2f. And why did it have to do that? Just for the fun of it, I guess. And then we're going to make another one for the y offset. And then go down here. I'm not going to really be messing with the 2D stuff anymore, so I'm going to get rid of that and clean this up. And we're not going to mess with these anymore, so I'll get rid of those. Now, I want to modify these to use our new versions of the variable, so I want to calculate our offsets as well. And go ahead and build, make sure there's no errors, jump back into Unity, run it, and now you'll see that our 0 point, and in fact those lines are now originating from the center of our texture. So you can see that they're fanning out. And then depending on where we are in the animation, they become more or less prevalent in various areas. But they're always fanning out from this center. Now, at first, because they were taking place, and we first noticed them when we converted value noise to use the lookup table, which is the same lookup table that our Perlin noise was using, my first thoughts were thinking it had to be something with the permutation table, or possibly the way that we're referencing with the U and V coordinates based off of this being 0. And I did a lot of testing and commenting and uncommenting and trying different random noises. And the problem always came up in a very specific way that got me thinking about it. And what I ended up doing to test my theory, besides trying different types of noises, was to take out our iterations. So if I remove the iteration and then just say do a sample at an I of 2, instead of going through and constantly incrementing I, we're just going to go through once with an I of value of 2 through our Perlin. So if I hit that and I go and run this, if it was a problem with either the U or V indexing or the permutation tables, we should see some sort of artifact inside of this noise, and we don't. And I tried it not only through just with the value of 2, I tried lots of different values. So I tried like 2, 4, 8, 16, tried some odds, and at no point could I get the artifacts to show up. So I knew that I had to look somewhere else for the cause of the problem. And what I hit upon was the fact that it's not a problem with anything we're doing. What we're seeing is an optical illusion. So if I go through here and I run again, once I start using multiple intervals and applying different octaves on top of each other, that's when the artifact becomes noticeable. And that got me thinking. What I figured out as it being an optical illusion and how that optical illusion is coming about is easier to show in Photoshop. So here we are in Photoshop, and I'm going to set my marquee select, and I'm going to create a grid that is going to simulate random noise. But because I don't want to put a whole bunch of different values, I'm just going to use black and white. So I'm going to duplicate this texture, scale it. I'm going to make it half as large as it was before. And then move this over here. Duplicate it again, copy it over here, merge it down, duplicate it, merge it down, duplicate it, scale it, reduce it by half again. Duplicate it, move. And I'm getting hung up in my cord again. All right. Let's do one last layer. Because I don't feel like taking this all the way down to the individual pixel level. But 4 layers should be enough to demonstrate the problem. All right, so right now, all we have is this black and white checkerboard. But if I start changing the transparency on these and reduce the transparency for each one to, say, about 25%, except the base layer, I'm going to leave that at black and white, what you'll notice is we start seeing something that looks like our artifact. We start seeing lines that appear starting at the center of our image and radiating outwards from there. So we've got one that cuts across the center horizontally, another one that cuts across vertically. We have this white line that is running diagonal from the lower left to the upper right. We have a black line that runs from the upper left down to the lower right. And as you continue this process more and more, we start getting secondary effects. So what we're seeing is an illusion caused by multiplying octaves that are exact powers of 2. So each time we're doubling the size of our octave, so we're getting these artifacts, and that's where all that's coming from. The illusion of them spinning around in a circle has to do with the fact that our noise is animated. So we're not using a solid value every time it's moving, so we just see it as it's shifting around in a circle. So because there's no problem with the algorithm itself, we have to find a way to work around it. And what I came up with is basically the offset. Right here where I offset the texture to force the illusion to happen from the center of our texture, it's just a simple matter of adding our texture size by the size of 2. So we take our texture size, multiply it by 2, and add it to our X and Y values. If I build this out and make sure we're doing our iterations still. Yep. And if we run this, we'll see that we don't have the spinning lines anymore.
Yeah, very nice. No lines at all.
Right. And then while I was doing this, you had mentioned you were curious why value noise looks the way it does, and you kept asking if that's the way it's supposed to.
Mm-hmm.
And I was trying to say, yeah, that's because of the way it samples the numbers. It's going to look that way. We don't get that nice convection look to it.
Mm-hmm.
But I just didn't feel like that was a good explanation. So while I was coming up with this, I happened to look at the checkerboard going, oh yeah, I can just show them that. What I mean is if we go back into our code and we turn off Perlin and we switch back to our value noise, and instead of doing iterations, we pick a single value for I.
Mm-hmm.
In this case, we'll start off with 1. And this is the one that we've shown before. And with a value of 1 and a value of 2, Perlin and value noise look almost identical, which is why you made the comment is like, well, if value noise looks exactly the same, why bother going through the other noises? The problem, or
Well,
it's not so much a problem.
Let me jump in there though. I said
Okay.
that in regards to the one look that you had right there. I mean, when we
Right.
go up to something that has numerous octaves that have been combined, that's different because value noise gives a result that I personally don't like because it's more like a fade one way. I mean, I do recognize that if you look very closely at the pixels, they are indeed shifting, but the overall look and feel is that it shifts and fades up and then fades back out.
Right,
Shifts
it's more
a
of
little.
a crossfade than
Yeah,
it
exactly.
is that nice organic crawling that you feel.
Right.
If we set I to a value of 32, this is what makes what value noise become very, very apparent. If we run now, hold on, am I on value noise?
I thought you were.
Yeah, me too. All right.
In the middle. There you go.
There we go. Trying to get the mouse to work. All right, so value noise. I0 iterations. We are iterating through. Yep. Okay, so we are using value noise. So let me check what version of value noise I'm using. Make sure I've got everything the same. Here, and there. And compare that with what I was doing. Yep. All right, so now, come on.
Were the texture sizes the same as well?
That might be different.
Because I know what you're going to show. You showed it to me off camera right before we started filming. And I thought it was a very good explanation. It definitely made me go, oh yeah, duh.
128 value noise there.
Is that what you're using on yours?
Yeah, the time's different, but I'm still using a 128.
Okay.
But I've been experimenting with so many things between this computer and this one, so the look that I'm getting is different from what I was expecting. But we're seeing the grid, but this one is smoothed out compared to what I had before, and I'm trying to figure out why. Because what I've got on my other one is that very checkerboard where I was showing you on my computer.
Yeah.
Where I get that very checkerboard look to it. And this one is blending.
Well, go ahead and stop and hop back in there. I mean, hop back into code.
Okay. Go back to value noise. And then look and try to figure out what's different between my version and that one. All right, so it's, let's see.
Well, again, I'll go ahead and just pause for a second while you compare these, because if you can give the exact same example, that would be cool.
Right.
So here goes the pause. Okay, Lee, we are back.
Okay, and I figured out what I was doing wrong. For demonstration purposes, I forgot I had changed this just to show what we're getting at a certain sample point instead of with all the lerping between our 8 sample points.
So for the record, you're kind of breaking it at the moment to
Yes,
demonstrate this.
I'm right. I'm breaking it to show how the samples work one at a time. I won't show each one of the 8 because each one of these 8 pretty much look like the same one.
Okay.
So they're just different colors at different times. So, but we're blending between them. So if we go ahead and go back to Unity and we run, we get a very checkerboard look. And what is happening is because we're relying on the lookup table, we're not using gradients. In essence, what the algorithm's doing is going, okay, everything between this point and this point is going to be one color. So we get a square that happens to be 32 pixels of one color. The next square is one color. Now, to alleviate this checkerboard pattern, that is why the purpose of the 7 lerps that we're doing.
But even then, the interesting thing is if you put that last blend in there.
Right. Once we get back to the last blend, because we're not doing any low-level smoothing or high-level smoothing at this point, we're apart from these 7 lerps, we end up with something that looks smoother, but we end up with something that you can still see the underlying squares where each one of them would be in this grid. And because we're shifting from a large patch of a solid color to another patch of a solid color, we're getting that pulsating feel as opposed to an organic crawl that moves across the pixels. Everything is pulsing on this grid.
Okay.
So this is one of the reasons why if we use the table lookup, while we do get very fast results, we don't get a very organic, nice feel to it.
And so now you can switch over and demonstrate Perlin at that exact same setting.
Same thing, yep. So what I can do is go back to Game Manager. So this is just a single iteration of Perlin with an I value of 32, which incidentally corresponds to, frequency. But that's going to be for a later video. So if we hit play, just one layer, we still get that very organic feel as it's sliding across the surface. It's not pulsating.
Okay, yeah, that definitely. I mean, as soon as you pointed it out before we started recording, I was like, duh, I should have realized that. But very cool.
But we also get some interesting little things that we can play around with, which is what I was kind of showing you, which you can probably see better now on your machine as opposed to when I was streaming it from my machine, which is if we iterate through, and up until now we've been starting with a value of 2 and going to something like 9 for our Perlin noise, but we can start at a much higher order. So we can start at 32, which means we're skipping the iterations that are 2, 4, 8, and 16. So we're skipping half the iterations. We're only going to be doing the iterations that are 32, 64, and 128. And 128 and the next one, 256 after that. So if we run this, just by making that one change, we can get a completely different feel to the texture. So it becomes a very soft type of look to it. There's no high frequency noise to it whatsoever.
Nice.
But that's one of the things I was trying to express was the fact that each type of noise has its own characteristic, its own feel to it. And then when we start getting into Simplex in the next couple of videos and we start demonstrating that, you'll see that while Simplex drives something that is derived completely different, and while it still is gradient noise, its output, the way it looks, is different than Perlin, and it is different from value noise. So it has a lot of the same characteristics, meaning that we can still control the number of octaves and the size of those octaves, the frequency of those octaves, and different characteristics that are shared between noise. Its fundamental feel and look and the way it animates looks slightly different than Perlin.
Gotcha. All right. So does that pretty much cover everything that you want to do in this video?
Yes.
So in the next one, we're going to start with some Simplex 2D theory.
Yep. So everybody go get your coffee. Simplex theory is complicated.
Awesome. All right. Well, thank you very much, everyone. And that will conclude this video.